So welcome everyone for today's special Gautam seminar. Today we have Gautam Satishchandran from Princeton University telling us about how horizons and modules.
Okay, thanks for the intro. Yeah, so how this happened, I was visiting Urbana and said I'll visit Chicago and
Just what I changed.
you guys haven't seen me enough, I guess, this year. Well, I thought I'd tell you about something that you probably have been at least hearing about to some degree because Dane's around and Bob is also around or something, but I don't know how specific everyone has gotten into all the details. So maybe what I'll do is I'll actually go through those details, and I think it might be interesting to most people. So this is based off of a series of papers started in 2022, well into 2023, and at the very end, I'll also tell about some kind of more recent work, again, more refining this title here. Okay, so sorry, one sec. So what's okay, well, what am I talking about? Well, this series of papers here is just going through a series of Gedanken experiments. Okay, so the first thing I probably should say is, well, these Gedanken experiments will ultimately be related to aspects of quantum gravity. Quantum gravity has been, well, it's been debated in this room or in this atrium, probably definitely in this building. It's been debated as early as, well, seriously debated as early as the 1950s or so at this very famous Chapel Hill conference. Okay. And so many people were at this conference in attendance. There was Wheeler, DeWitt, well, Feynman was there as well. And really, well, they were really debating, what the fundamental, structures are of quantum gravity. How would one formulate such a theory? And you can go online and print out the transcript for this conference, and it's really interesting to read. And what's mostly interesting is Feynman, for most of this debate back and forth of what the basic rules would be of such a theory, was kind of uncharacteristically quiet. Right? He doesn't say anything for most of this debate, and then at some point he just kind of interjects. And I imagine when I read it angrily, he didn't seem happy, and he said, really, I don't know what the basic rules are of of such a theory, but maybe what you should do instead of going from this kind of bottom up approach, to also consider situations, to probe the aspects of this theory where both gravity and quantum mechanics play an essential role. Okay, and then use the well understood rules of the quantum theory to infer aspects about the fundamental theory. Okay, and so like you are probably wondering, he was asked, I think by Wheeler, in this dialogue, he was asked, well, can you give just one example of such a situation? And kind of off the top of his head, he made up the following example. So if you take a massive body and you put it in a quantum spatial superposition of two spatially separated states, so half probability of this body being on the left and half probability of this body being on the right, well, Feynman just asked everyone in attendance, well, what is the gravitational field of such a body? So, and Feynman answered the question. He just said, well, the gravitational field would presumably be, in a spatial superposition of half probability of it being, as depicted here, or half probability of it being supported over on the right. Okay, and so Feynman just kind of Feynman just pointed out, well, even in this very simple situation, one needs, quantum gravity to describe the situation. There is no sense in which the gravitational field can be classical in this regard. Go ahead.
Maybe this might be later in the talk, but I guess the question I usually have about such setups is if you don't have the sort of theory of the gravitational field.
Yes.
What does it mean to say it's a superposition of this field and that field?
Well, so Feynman was just asking, what would the gravitational field of such a body be? So you can postulate whatever kinds of things you want. Everything I'll be talking about is basically going to be applying to linearized quantum gravity coupled with matter fields, right? And to like so very low energy quantum gravity. But I'm not going to be talking about anything more complicated than that. But in this particular case, Hyndman was just asking, I mean, you can draw pictorial diagrams of this sort to say, well, it's presumably of this nature. I mean, it's half probability of the body being here and half here. If you're asking what theory I'll be using later in the talk, the theory would basically be of linearized quantum gravity coupled to quantum matter.
I thought gravitational field by definition means that gravity is flat. These words mean nothing. What does it mean?
Well, there is a
classic notion, like electromagnetic.
No. I mean, there is a sense in which, I mean, and if you consider in linearized quantum gravity, you can consider a source that is in a quantum spatial superposition.
Okay.
And so then if you solve that equation, then the perturbed metric will also be at leading order of G Newton, a super in a super.
Yeah, but this is the expectation value of field in state. And that if it's enough to talk about that notion, that means by definition that the fluctuations in that quantity, which is quantum gravity, are not important.
No,
It's all look, it's lawyer, my lawyer.
Yeah.
All I'm saying is that I just don't understand what is the quantum gravity means the gravitons, the scattering, the loops.
No. In this context, I just mean that the literal gravitational field, it is in a superposition. It's half probability of the gravitational field being in this configuration and half in this. Yeah, I would say that there are no gravitons in this depiction at all.
Yeah.
But if you say gravitons are quantum gravity, then you are not allowing such.
No, wait, I said the opposite. That the words you said now are situation. So the quantum effects are important, but not quantum computation.
Well, I would say whenever the gravitational field has, different probabilities of being in different macroscopically obviously different situations, then it sounds like your lawyer needs to talk to my lawyer.
Give me some.
Okay. Okay, so go ahead.
Sorry, just derailed the part, but just say for EM, you would want to imagine you treat some particle somewhat semi-classically as like or you take a wave function of a particle like two delta functions, right?
Right.
And you're imagining some coherent states of EM.
That's exactly what I'll be doing in a second. But again, and that'll all just be for ease of calculation. That's not going to be essential for what I'm describing, but it'll be easy for ease of calculation. So if you want to describe exactly this kind of scenario, you would want to consider a scenario for the electromagnetic case where the charge current fluctuations of the body are negligible. And therefore the electromagnetic field sourced by the body, the quantum electromagnetic field is a coherent state of the kind that you suggested. And so then the body being in a superposition of half probability of being here and here in the electromagnetic case would literally correspond to a superposition of coherent states.
Yeah, I think that's what gravity, but you need someone to be able to talk about.
Yeah, so the same object would right. No, that's the exact same thing, right? Because if the stress energy of the body has negligible fluctuation, then the same exact calculation, but now you're solving for the perturbed metric as opposed to the vector potential would give you that the perturbed metric, the state of the perturbed metric would be a coherent state. This is a trivial, this is just a statement that. So, radically. This is the classical number. The solution to this is H2 is equal to the vacuum plus the required speed. You have a state which is the superposition of vacuum, then you're going to sort of superposition. And you could replace H with an A and do this. Okay, so what's the point? Well, in the spirit, well, basically in the same vein, and we'll see how much we get through based off of what the discussions. What we'll basically see is that these same kind of Gedanken experiments that Feynman was thinking about is going to show us some relationship between horizons and, in particular, decoherence of quantum superpositions in Derek's theory. Okay. Okay, so before getting into the when did we start, by the way, just so I know when we 12:10. Okay, so before getting into the case with the horizons, it's actually very nice or going to be important to just consider the case of flat space-time. So let's consider a Gedanken experiment first in flat space-time, and let's do the electromagnetic version of the story. So the concepts are more familiar, and we can follow along. Okay, so consider an experimenter. Well, this is a Gedanken experiment, so I need to consider an Alice. And Alice's PhD thesis is to consider a quantum spatial superposition of the kind that Feynman was suggesting. Okay, so I'll explain how she's going to do that in a second. So she's going to then take a charged body and make a 50-50 spatial superposition of the kind that she was just suggesting. And this particle is going to have some charge, of course, as I was just telling you. Okay, so that's already a big deal. I mean, she should get a Nobel Prize just for that alone, but she's going to go even further. She's going to maintain the superposition for her PhD, I guess, for her whole PhD thesis. And then at some predetermined time, let's say it's her committee meeting, she's going to be told, recombine your particle and check for its coherence. Okay, so I'm going to go over the exactly how she would do that, but does everyone understand this bullet point? Okay, so what did Alice have? Well, she started her PhD way down there, and let's say if her particle had spin in the x direction, she could pass it through a Stern-Gerlach apparatus and make a 50-50 spatial superposition of, let's say, spin up and in the z direction and gone to the left, and spin down in the z direction and having gone to the right. She then maintains that. I mean, that's really hard to do. She's going to maintain that for a very long time. This is the time of her committee meeting. She's being told, you got to reverse your Stern-Gerlach apparatus and send your beams back in. When they pass through the reversing Stern-Gerlach apparatus, she's going to recombine. She wants to graduate within a time TA, and she's going to then check for the coherence of her particle. Okay, so how could she check for the coherence? Well, if her particle initially had definite spin up in the x direction, when she recombines the particle, she better have definite spin up in the x direction again, a coherent superposition of up and down in the z direction. And so then she could just measure the x spin. If she ever sees down in the x direction, she knows she's decoherent. She doesn't know maybe how much. She'll have to do a PhD again to check to get statistics, but she knows she's decoherent at least to some degree. Does everyone understand Alice's protocol? Okay. Okay, so why is she worried about this? Why is she worried about not graduating? Oh, let's say she doesn't graduate, I guess, if she loses coherence. Well, there's another experimenter, Bob. And this Bob is not Bob Wald. This is a skilled experimentalist. And what he's going to do is he doesn't want Alice to graduate. So what he's going to do is he has a particle, let's say, in a trap that's not correlated with Alice's superposition at all. Okay. And what he wants to do, and he doesn't want to get caught for destroying Alice's experiment. So what he's going to do is he's going to go to a different building, at space-like separation from Alice's recombination. He knows when her committee meeting is. At the time of the committee meeting, he's going to open his trap. And his particle, due to the superposition of the Coulomb fields that are set up way over there, I'll show you a space-time diagram in a second, his particle will become deflected differently and therefore entangled with the different positions of Alice's particle. Okay, so let me show you a diagram if you are, if it's not following along. So Bob is over here in a different building. He has a particle in a trap, initially completely unentangled with Alice's superposition. He's going to open the trap at some predetermined time. And his particle is going to get, Alice's Coulomb field of the particle having gone to the right, or the Coulomb field of Alice's particle having gone to the left, are all set up in this region. Alice or Bob is going to become entangled with, the which path Alice went on by his particle getting deflected. It's going to get deflected more if it's feeling the Coulomb field of the particle on the right, or it's going to get deflected less if it's feeling the Coulomb field of the particle on the left, of Alice's particle on the left. And therefore, the positions of his particle are now going to become entangled with Alice's particle. Go ahead.
It's like our very semi-classical conductors. Like I would imagine, even if you compare to very tight wave packet early on,
Yeah.
like this particle is going to spread out.
Oh, for sure. And that's going to be essential in a second. So the wave function spreading of the particle due to just regular wave function is going to be dependent on the mass of the particle. That's not so important. I mean, I can make it, in this particular case, we have to cover all cases. So for example, if Alice's charge is big enough, or the size of her superposition is large enough, I can make the deflection of Bob's particle large enough that it overcomes any wave packet spreading effects. So you're landing on something that is going to be important, but you're landing on something. Just give me 1 minute, and then does anyone else have any questions about this setup? What Bob is doing and what Alice is doing. Okay, so you should be, you may not have questions, but you certainly should be upset about this situation. And the words you might use to explain how upset you are the following two here. Well, there's the notion of so-called complementarity. So if Bob can obtain which path information in the sense that he can become correlated with the positions of Alice's particle, then his particle is entangled with Alice's particle. Well, that's a tautology. And if Alice's particle, and therefore Alice's particle must be decohered to some degree. Okay. So if he's correlated with Alice, that means Alice is correlated with Bob, and therefore Alice's particle must be decohered to some degree. Okay, but obviously by causality, and this is the reason you're all upset, hopefully, Bob should not be able to influence the coherence of Alice's particle at all. Okay, go ahead.
If Bob never measures part, like let's say that it's in some isolated box and there's enough room for those trajectories to spread out without interacting with the size of the box. Bob never measures it, then what else particles still be decreased?
Yeah, the measurement played no role in what Bob was doing. He just opened a box, and the particle became entangled with Alice's particle.
Now
You could, yes, there's measurement plays no role in it for Bob. We want Alice to measure the spin at the end just to check for coherence, but for Bob, he just needs to open the box. He could walk away.
Well, he would need to see which path it follows, so he could tell
No.
us the coherence, right?
No. The statement is that Bob's particle just needs to become entangled with Alice's particle. In principle, Bob could measure and find out which path he went on, but that's not relevant for whether or not Alice is decoherent. Right, just two quantum systems becoming correlated will lead to decoherence, regardless if you go ahead and measure one of the systems. Okay. So is everyone confused in the right way? Okay. So what was alluded to before, and what is certainly true, is that I haven't fully told you the whole story. And what I really missed is, the coupling to the electromagnetic field, the full, all of the constraints from the electromagnetic field. In particular, Alice's experiment. So what is the task Alice is given? For some reason, okay. So the task Alice is given is that she needs to recombine her particle within a light travel time from Bob. Okay. which means that she has to accelerate the branches of her superposition back together fairly quickly within a time t, a, right? And so she's coupled to the electromagnetic field, and she might just completely all on her own decohere her superposition by the emission of entangling radiation, irrespective of Bob. Okay? And Bob's particle, well, as was alluded to before, is coupled to the electromagnetic field. And he's trying to make a measurement of the electromagnetic field locally in his region. And since there's vacuum fluctuations of the electromagnetic field, by Lorentz force, there will be vacuum fluctuations affecting his particle measurement. And so he's got to measure the displacement of his particle beyond a vacuum fluctuation of the particle of the electromagnetic field. Okay, so it's not obvious these two are going to, conspire to solve the story, but I need to take these into account. Okay. Okay, so and this is going to be the most complicated calculation we'll do in the whole talk. Let's calculate first the amount of decoherence due to the entangling radiation that Alice must suffer on her own. Okay, so if psi1 and psi2 correspond to the coherent states of the radiation of Alice's particle going on the right and going on the left, then these are the electromagnetic states of Alice's particle going, the radiation emitted by path 1 and path 2, then you can just straightforwardly calculate the decoherence. The decoherence of Alice's particle is related to the orthogonality of these radiation states along path 1 or path 2. Okay, so this decoherence is, it's 0 if these states are if Alice radiates nothing, if it's the radiation states of the vacuum, then it's 0. If she radiates orthogonal states, then the decoherence is completely 1. Okay, and you can calculate that by just computing the expected number of photons in the difference of the radiation state. So you take the radiation along path 1, you take the radiation from path 2, compute their difference as a quantum state, and you can compute the expected number of photons. These are what we call entangling photons. They're the photons that know the difference from going along path 1 and path 2. Okay? And it's very easy to estimate this for this simple case of just Alice accelerating her superposition together. By kind of Larmor formula type estimates, you can get that the expected number of photons emitted during this process just goes like the charge times the distance of the body divided by the time that I take to recombine the particle that Alice takes. Okay, so even in the absence of Bob, in order for Alice to maintain coherence just on her own, we need this expected number of photons to be less than 1. So to make sure that she doesn't get decoherent. Okay, if she emits an order 1 number of entangling photons, she will be completely decoded. Okay. So what does that mean? Well, she's got to recombine the particle slowly enough on her own just to avoid any decoherence. Okay. Is everyone following along? Yeah.
I think the thing we've got here is also what gets treated classically, what's quantum, and sort of what justifies the semi-classical approximation.
So the only statement here is that it's not a so the only approximation I'm making here is that Alice's particle has negligible fluctuations in the charge current. That's just so that I can make a simple calculation. So in that case, if the particle has negligible fluctuations, so there's a wave function of the particle, then there's a charge current of the body. The charge current of the body, if it has negligible quantum fluctuations, then the electromagnetic state it sources is a coherent state. So those are all of the statements that's the full calculation. So now what I'm doing is I'm calculating, this is the coherent state of a body with negligible charge current fluctuations going along path 1. And this is the coherent state of a body with negligible charge current fluctuations going along path 2. That doesn't mean that there's no wave function to the body, just that the charge current fluctuations are negligible. Which field? The electromagnetic field? Yes.
are.
For quantum field theoretically, yeah.
Quantum field theoretic, like this is in full QED, for example. Yeah.
They're not small around the back, it's large.
Oh, yeah, this is that's correct. Yeah. This is, well, it's in the Fock space in general, but it'll be some coherent state. And it's not a one particle state, if that was the question.
So you're just putting like a word line, you're putting a delta function with charge Q, like J equals Q delta function with this path. And this size just a coherent state with this J. So like AU.
Yeah, it doesn't have to be so singular as a delta function. You can have any smooth charge current you want, but I'm saying that the 2-point function of that, the connected 2-point function of that charge current is negligible relative to the kind of 1-point function. So that's the statement that's the approximation in which you can just, the electromagnetic state is a coherent state.
So the only thing that is classical is that you have these two word lines that are kind of fixed. All the rest is quantum.
Yeah, well, classic, yeah, in the sense, it's, it's not really classical, it's just we're making like, you can add the charge current fluctuations of the body into the story, it's just not going to be relevant for Bob to obtain which path information if you want the body to jiggle a little bit in the charge current. Like, it's not going to help Bob all that much. The main contribution is with respect to, the charge, the 1-point function of the charge current, is that's what we're making as an approximation. Okay, so Bob, well, yeah, we'll see what I get to. But this is all good. So Bob's particle, if Bob is making a measurement locally in his region, and his particle is buffeted around by these vacuum fluctuations I mentioned before. And it's not hard to estimate how big they'll be, but just by kind of standard, it's coupled to by Lorentz force, it's coupled to the electromagnetic field, and roughly it'll be of order, and you can really make this much more precise, but his particle gets buffeted around by roughly the charge to mass ratio of the body. Okay, so what ends up happening is when you couple to the electromagnetic field, the charge, the body, the wave function of the body will spread out automatically up to a charge to the mass ratio of the body just on its own. Okay, so what Bob needs to do is he needs to get his displacement of his body bigger than the amount he gets spread out just by vacuum fluctuation. And just to kind of, so that is going to give him a limitation on, he needs to do this within a certain amount of time in his lab. And what you find is that Alice's charge and her size of her superposition must be bigger than the distance between Alice and Bob. And let me just give you the basic point, which you can show by just, simple back of the envelope type arguments, that these conditions cannot be achieved within a light travel time. So the basic point here is that, if I go back, let's consider the case where I give Alice a really, really long time to recombine the particle back together, then the basic point is, so then Alice is going to maintain coherence when she gets, to the tip of this diamond. That's exactly the situation. So I'm now shrinking the amount of time that Bob can integrate his experiment. And the statement is that Bob cannot, integrate his experiment and get significant which path information beyond the vacuum fluctuation. Okay. Whereas in the cases where Alice does, in the cases where Bob could get, so let's say you allow him to integrate this over a very long time, that shrinks Alice's diamond, and that forces you can show will then force Alice to decohere herself on her own. She's got to recombine the particle far too quickly on her own. Okay. Does this intuitively make sense? Go ahead. So delta X is the displacement of the particle, which is related to the charge of Alice's particle, right? So the vacuum fluctuations is related to, the size of the vacuum fluctuations are related to the charge to mass ratio of the body, right? Of Bob's particle.
His displacement also will become more and more
Yeah.
gradual.
Oh, you make.
right? Because like the charge to mass ratio enters in the coupling into how much you get to split. So if you want, so you might be, I mean, upset by these, or, you might wonder if there's a more rigorous argument than the ones that I just mentioned here. And just let me just say, well, for a completely general and rigorous argument for any measurement that Bob could do at space-like separation, that's what was the subject of this paper that I've given here. I won't have time to go over that in this talk. I certainly don't have time to go over it in this talk. But let me just give you the lesson that, well, is going to carry us through to the rest of this talk, which is that Alice basically must decohere herself by emitting entangling radiation at least as much as any Bobs could decohere. So what we showed is one particular example of Bob making a measurement at space-like separation. What this more general argument really shows is that you can populate all of these Bobs at space-like separation and try to get them, put one Bob here, make maybe another joint measurement over here, and so on and so forth. And Alice will always decohere herself by emitting entangling radiation more than any Bob could obtain at space-like separation. Okay, so that's what the general argument shows, and this one particular example is an instantiation. Okay, so in particular, if I give Alice a very, very long amount of time, so I let her recombine arbitrarily slowly, she will be able to maintain coherence. And well, conversely, the Bobs at space-like separation are getting less and less, time to be able to integrate their experiments and get significant Witch path. They're getting pushed out farther away and from Alice's recombination. Okay, so that was the story as of not this last December, the December before that, 2022. And I was happy to be done with that project and move on to other things. And Dane suggested, well, fortunately, or I was puzzled for a long time. Well, what if the Bob was behind a black hole? Okay. And that sounds, I think I remember laughing at the time. That sounds ridiculous, but just humor me for a second. So suppose a black hole is present and you have a Bob or a sequence of Bobs, and these Bobs are definitely not Bob-walled. I'm not, these are expendable Bobs. So I'm just going to throw them all inside the black hole. I'm going to allow them to make arbitrary joint measurements of the electromagnetic field in the interior of the black hole. Alice is outside of the black hole. And now she's as far away as you like, and she can do this experiment. She's not time limited at all now. She's going to do the experiment for as long as she likes. And I'm going to give her all the funding she needs to, keep her way outside the black hole and do the experiment for as long as she likes in the exterior. So as you should, be thinking along these lines, well, the Bobs cannot causally influence Alice at all. But if Alice's superposition is maintained for an arbitrarily long amount of time, the Bobs in the interior, and again, I'm just going to keep throwing more and more in to accumulate arbitrarily good Witch path information on Alice's superposition in the exterior. Okay, so let me give you a picture. Well, this is the space-time diagram of the black hole I want to consider. This is the collapsing star that created the black hole way, way, way in the past. This is almost irrelevant until basically the end of the talk. This is the singularity. That's just to remind you that there is a black hole there. That's also not going to play any role. This is the horizon of the black hole. That's going to play a very important role in this talk. And what I have here is Alice. Now I've given her a rocket or something because I don't want her to be falling into the black hole and radiating. I want to do as optimal an experiment as I possibly can. I'm going to have her give her a rocket and basically put her lab at some fixed distance from the black hole. I'm going to have her, she's going to do the separation just as before, make a superposition in her lab of the same kind that I was describing. She's going to maintain that superposition for a time capital T. And then after some amount of time, she's going to recombine the superposition back together and check its coherence. She's going to do all of this arbitrarily slowly. So any time scale that you like, I'm just going to have her do slower than that. And I'm going to make it so that, well, she's at some fixed distance so that she's not radiating at all. I'm going to try to get it so that she basically radiates nothing to infinity. And I'll describe that again in a second. Is anyone confused about Alice? Go ahead. Yeah, so well, if the body was in free fall towards the black hole, she'd be radiating to infinity. But one statement, to make it slightly more obvious, is there's a time-like killing field, and she's going to be following the orbits of the time-like killing field in the exterior of the black hole. So a stationary body outside of a black hole does not radiate at all. There's no electric field radiation out to infinity or into the horizon. And I'll show you the explicit solution in a second. Okay. So the question or the picture that you should have is, or what Dane was asking was, well, what if I throw a bob in there? And so there's some superposition of Coulomb fields that Alice is generating here that's going to be inside the black hole. Why can't I put a bob in there and have them measure this, get some which path information on Alice's superposition? And this will, well, the same kind of question is now arising, but now I'm not limiting Alice's experiment at all. Okay? Is everyone confused again? Okay, so now we're just going to do a calculation. So what we're now going to show is that black holes indeed will harvest which path information on quantum superpositions in their exterior. And in particular, the presence of the black hole forces Alice's particle to emit soft photons, and in the gravitational case, gravitons, into the black hole, and is going to result in a constant rate of decoherence. This has to be true based off of the principle that I told you before, which is that if the bob can obtain any which path information, Alice must be decohered by a commensurate amount. Go ahead.
How does the rate of decoherence depend on the distance from the black hole?
Well, why don't I just do the calculation and then I show you that. Because it's not going to, I don't know, remember off the top of my head right now. It depends strongly only because the intuitive sense is that the bobs are trying to get which path information inside the black hole. So, if I am very far away, it should depend strongly on the
6 power Indian.
Yeah, 6 power. That's right.
The rate in QED.
Okay, so mathematically, what do I want to calculate? Well, we're going to do the same exact calculation that we were doing before but now I'm going to do this process so slowly. I'm going to do the separation, maintain the superposition and the recombination so slowly, slower than every time scale of the problem. Well, slower than the time scale I gave you before, but maybe she's moving her superposition through a gravitational field. I'm going to make it slower than any time scale associated with the curvature of the space-time. And the basic point is that I can ensure that she radiates nothing to infinity. That the radiation to infinity is exactly the vacuum, or as close to the vacuum as ever. She radiates no which path information. But what must be true then in this situation is that and what we'll find is that she cannot help or avoid radiating into the black hole. And in particular, the decoherence, and now I'm going to attribute it to the presence of the black hole, cannot be zero and must also grow with the time I make the superposition, based off of the considerations before. Okay. So now we're just going to calculate. Is anyone confused about what I'm calculating? Okay. So I don't know what we'll get to in this talk, but so maybe I'll just say this bullet point now. All of the steps of this analysis will generalize to any quantum superposition in the presence of any killing horizon. So in particular, cosmological horizon, you'll get the exact same calculation, which is also always going to decohere the superposition at a constant rate. And eventually, the presence of any such horizons will completely decohere any superposition in its exterior. Okay. So now we're just going to do a calculation. So it's a little bit easier and to look at, well, it's hard to draw angles on a Penrose diagram. This is a little bit easier to see what's going on. So this is Alice's experiment, which I'm, doing over out in the exterior. This is the black hole now that I'm depicting, where V here is the affine time along the black hole. It's related to maybe the more usual, what you might be familiar, the killing time or the time, the T here, which is the time as measured in Alice's lab by an exponential factor. And so it'll be more useful for most of this talk to work in the affine time, but we're in the end of the day, when we make estimates or something, we'll go to this killing time as measured, which is the time in Alice's lab. The cross sections of this black hole are spheres. Capital A indices will refer to angular indices on the sphere, and this R is going to be the radial distance off the horizon from the black hole. Okay. Okay, so now let's do a warm-up problem. Okay, so what is this warm-up problem? Well, we're gonna, instead of considering a superposition, let's just consider a single body just to start with. And I want to know what is the radiation from this single body. Okay, so let's consider a warm-up problem where I now have a single body where I initially have at some position R equals D, and then I'm just going to slowly displace it to a new position, R, by a displaced amount little d. Okay, and I just want to know, I'm going to do it arbitrarily slowly. I'm not going to radiate anything to infinity. I want to know how much or what do I radiate into the black hole. Okay. And so this is, well, what I want you to think about. Well, I have a body here. I'm going to slowly displace it to a new position and hold it there at this new position. Okay, and I'm going to do this arbitrarily slowly. Okay, so well, it might sound like that sounds like a complicated problem. You don't have to solve Maxwell's equations in a black hole background, but it's actually very easy if we look at Maxwell's equations on the horizon of the black hole. Okay, and what Maxwell's equations on the horizon of the black hole shows or relates is the Coulomb field on the horizon of the black hole. This is the radial component of the electric field on the horizon. It relates changes in the radial component of the electric field to this horizon radiation. The reason it's horizon radiation is the radiation is propagating radially, it's oscillating transversely, and in these coordinates, that would be angularly. Okay? So the divergence is the divergence on the sphere. And if I take the divergence on the sphere of this electric field, that's related to any changes in the radial component. So this is exactly what I need. Alice is moving a charged body. She's going to be moving and changing the magnitude of this radial component as registered on the horizon. Okay. So for a static body, as was asked earlier, this EA vanishes. The horizon radiation is zero. So that's intuitively, hopefully clear that if I have a static body, it radiates nothing, well, to infinity or into the black hole. Okay, and in particular, the radial component of the electric field, well, it'll have angular factors, angular dependence depending on my relative position to the black hole horizon, but its magnitude is what you would expect. It's just the charge over the distance from the horizon squared. Okay. And well, throughout this process, again, I'm displacing this body arbitrarily slowly. So throughout this process, Maxwell's equations tells me that the electric field as generated on the horizon from this process is arbitrarily small. Okay. But I can't set it to zero. The reason I can't set it to zero is because, well, if I integrate this equation, the right-hand side is the change in the radial component of the electric field. The change in the radial component as registered on the horizon of the black hole, well, the horizon is some finite surface. If I move a body from one position to the other, the change in the radial component will be non-zero on the horizon. And that means that the total integral of the electric field as on the horizon cannot be zero. So I can't approximate this electric field to be zero. Okay. but that's not any cause for alarm at this point. And this other bullet point is just not necessarily any cause for alarm either. If I can also tell you what's going on with the vector potential. So if I have the electric field, I can write that in terms of the vector potential as the derivative of the vector potential. Okay. And if I then, well, this implies, well, if the integral of the electric field is not zero due to the change in the Coulomb field on the horizon, that means that the vector potential must suffer a permanent change on the horizon, right? So I'm just plugging this formula into this formula. Here. Okay, must suffer a permanent change on the horizon between early and mid. And just to digest that a little bit further, well, what I'm really saying is if I have a particle that I slowly displace to a new position outside of a black hole, no matter how slowly I displace it, the vector potential on the horizon must suffer this permanent change. And recall, changes in vector potential are gauge invariant quantities. So this is, and the change in the vector potential is proportional to the change in the Coulomb field as registered on the black hole. Okay. So now, well, I've just told you what the vector potential looks like. And now all we have to do to understand, well, these coherence issues that I was telling you about is we need to compute the number of horizon photons as produced in this process. And well, this bullet point is just a true statement that is worth well, explaining at least in one bullet point, which is that if you give me any classical solution to Maxwell's equations, the corresponding quantum state of that is a coherent state. The expected number of photons in a coherent state above any chosen vacuum is given by the norm of the classical solution in the corresponding Hilbert space of above that vacuum. So what does that mean? Well, if I'm interested in the expected number of photons in some coherent state generated by a classical solution A, well, that coherent state lives in a Hilbert space. In particular, it lives in a Fock space. I can look at the one particle Hilbert space of that Fock space, and I can take my classical solution and just compute its norm. Okay, these are just equivalent formulas. Okay, and the reason why that's nice is, well, now I have a formula for computing the expected number of photons as produced in this process. So what is our vacuum state? So this is, well, if you were worried about which vacuum state I'm choosing, this bullet point is for you. If you're not worried, then don't worry about it. So the vacuum state should be the vacuum state of a black hole formed from gravitational collapse. That should be the Unruh vacuum. Anyone who's worked with the Unruh vacuum on the future horizon of a black hole would be worried about this calculation at this point, except for it's not hard to show that at low frequencies, which is the frequencies that I'm looking at, frequencies less than m, or 1 over m, the Hilbert, the Unruh vacuum on the future horizon is equivalent to the Hartle-Hawking vacuum, and the norm of any vector potential on the Hartle-Hawking vacuum is really simple to write down. Okay, so the basic point is I have a formula for you for this expected number of photons for this particular process that Alice is considering. Okay, and what is it? It's you just take the vector potential, you compute its Fourier transform. That gives you the Fourier transform with respect to affine time. You square it, you integrate over positive frequencies, and you integrate over angles. Okay, so this is now the formula for computing the expected number of photons in this particular process. Okay, so this is pretty well going to be an elementary calculation. So the change in the vector potential is not zero, which means that the Fourier transform at low frequencies must diverge like 1 over the frequency, like the Fourier transform of a step function, which means that the expected number of photons in this process is logarithmically divergent at low frequencies. Okay. So what's the basic point? So what am I saying? If you take a charged body and you slowly displace it to a new position and leave it there forever, you'll radiate no photons to infinity or negligible photons to infinity, but you'll radiate an infinite number of soft horizon photons into the black hole. Okay. So I'm, as I mentioned earlier, not interested in taking a body and displacing it and leaving it forever. I want to do an experiment. I want to bring the body back. But if I displace the body back to its original position after a time t, then the expected number of photons will be finite, but large for large t. Okay. Yeah, so you don't get, well, in the star case, in the case of a star, so in the case of a black hole, what was very important was this relation. So you, on a time-like surface, such a relation does not hold. There will be no constraint like this. And more to the point, you can just do the calculation in the case of a star, and it's effectively like in the Minkowski case. If you just recombine arbitrarily slowly, then there is no radiation out to null infinity, and there's no production of photons into the, like, you should think of this as that on the horizon of the black hole, me registering different Coulomb fields is kind of forcing the emission of photons into the black hole. Like, it's like these photons would not be thought of as photons if it wasn't for the black hole. Like these photons are things that hit null infinity or go into a black hole, right? If the black hole wasn't there, then these would not be produced. Okay, so now we can do a calculation and cut me off. How much time do I have? 15 more minutes? Yeah. Okay, great. So now we can just do a calculation. So with the expected number of photons, now I want to do this case where Alice, displaces the body for some amount of time and then puts it back to its original position. Well, that's going to diverge logarithmically, as I mentioned before, the number of photons produced in this process. And if I write that, well, logarithmically in affine time, and therefore in the proper time of Alice's lab, it will grow linearly in the time that Alice has displaced the body. Okay. So, well, I just told you what happens to one branch of the superposition, but the same happens to the other branch of the superposition. She's doing making a superposition of two displaced particles. In that case, both will radiate these soft photons to infinity, and it's not hard to see that the expected number of photons in the difference of these radiation states will also grow linearly in the time that she maintains the superposition. So what is Alice doing? She's taking a body, she's making a superposition, and she's just holding it in the presence of a black hole. Okay, and as T increases, the superposition is becoming less and less coherent in time. And she's not radiating anything to infinity. The decoherence entirely due to the presence of the black hole is given by the exact same calculation I told you to do before, but now I don't need to, now I only need to take into account the quantum states on the horizon of the black hole. And after the emission of an order 1 number of entangling photons, which is going to happen after some finite amount of time, the superposition will just be completely decoherent. Okay. So now we can just estimate. So the first thing I should say is, I mentioned, well, the people are making these spatial superpositions in laboratory or trying to at the moment. They don't need to worry about this effect. Okay, so if the sun was a black hole and we were doing an experiment on the Earth where I took an electron and superposed it over a meter, then this electron, we'd need these experiments to finish within 10 to the 43 years. This is much much faster than the black hole evaporation timescale for such a black hole, but still, we don't have funding for so long anyway. So, but if you if Alice instead did this experiment at the ISCO, so the innermost stable orbit of the black hole, then she would have to finish her PhD in about 5 minutes. Okay, and this is really because of the question that was asked before. This depends strongly in the distance from the black hole, like d to the 6. Okay, and well, a similar analysis of the linear, well, you can do the same analysis for the linearized Einstein equations in the exact same way, and the decoherence rates are slower. I mean, that's only because of, well, you're now getting decohered by gravitons, and we did this very cute estimate in the essay, which is if you take the Earth and put it in a quantum superposition, spatial superposition separated by its own radius, and the sun was a black hole, so it's still very far away, then it would decohere in 10 microseconds. And I think we have this in the paper that says, it wouldn't be so easy to put the Earth in such a super. Okay, so.
So you say conceptually, you can tell whether something is a black hole or a star while staying entirely far away from it.
You would say far away, but the decoherence time is you're not decohered quicker than the light travel time between you and the black hole, or the you and the surface of the star.
No, but
so there's
I
no.
don't understand. You said that this whole effect does not exist for a star.
Yeah, that's what this bullet point
Okay,
is about to get to.
so
Yeah.
you can do this experiment staying light year away from the black hole.
Yeah.
And still tell whether it's a black hole or a star. That thing that you're light away.
Well, so you make, so it depends on what you mean by do the experiment. If you make the superposition
Well,
and well, let me say, so if you make the superposition, then the Coulomb fields need to go and register on the surface of the black hole. And as soon as they register on the surface of the black hole, they will start to decohere you. It won't be appreciable decoherence until you wait a significant amount of time that depends strongly on the
Okay,
distance.
but these are the details.
Yeah.
If you have enough time. I mean, there are other
Yeah.
problems, of course. It's not just you and.
Oh, yeah, no, there's lots of,
some other
yeah,
stuff,
yeah.
other effects, but
Yeah.
conceptually you claim that I can tell it.
Yes, yes.
If all there is me, what do you call it, Alice,
Alice,
and
yeah.
the black hole, and there's just nothing else.
Yeah, yeah,
You
exactly.
can tell if you live long enough
Yes, yes.
that that thing is a black hole,
Yes.
and not a star.
Yeah.
Things kind of surprising.
Yeah, I'd say this whole thing is kind of.
But it would be, we need a time wait rather than you would say to preserve.
Yeah, yeah, I mean, it's not like, it's not,
What?
then the light travel time.
Okay,
is
so
like,
If you are a 1 light year away,
So what?
it would take like 400 years for you.
Okay, so what?
You could see. it.
Well, I mean, I think he's commenting on the surprising aspect.
What the, like, the
Hawking radiation.
well, I mean, like, there's radiation from O2, right? The question is how do you know if it's
Oh, I
radiation
see.
because of
Yeah.
whatever. So I guess, okay, the question, is there some other earlier known effect that can tell you while staying up to the far distance from spherical
Earlier historically, or?
So is there another known effect that has this property?
The thing is shining.
I don't understand the question.
Can you check if the thing is shining or not? I mean, that's the way to tell.
Well, I don't understand the
Well,
question.
I don't understand the shine.
Well,
I
okay,
mean, if you could just see from light.
It's just not that hard to visually distinguish a star from a black hole.
You mean,
When I look up at night, I see a lot of stars, right? And there might also be some, but I can tell.
this seems less productive. Than the earlier one.
But you really are losing a little bit of radiation in the black hole. That's what's the difference. And when you had a star, if you take your charge and move it back, the whole Coulomb field of the star goes back to what it was. And nothing is sort of lost or radiated, but that does not happen in the part of the Coulomb field that was inside the black hole. Sort of
Doesn't come back.
you really lost something. So I mean, there's a genuine difference. You know, which is kind of underlying this, this effect. Not a very big effect difference.
Is there also like a kind of phase condition between star and black hole with a blue shift on the horizon? What impact? Is that playing a role at all?
There is a relationship to blue shift a little bit. I mean, in the sense of if you had a, well, let me answer your question at the end. I mean, that's going to derail things a little bit. Yeah.
The color is responsible for the dimension.
Okay.
To the parameter from the top and the hole.
Yeah.
It would be a shot that somewhere.
So the sharp things I can say is the following. So if you have any eternal star, so if you just do this same calculation for a star that's existed forever, then you will get no decoherence. There's one caveat, which is that if you take something and you form a star, like collapse it, but then abruptly stop it right outside of its Schwarzschild radius, like I guess is related to the fuzzball program in some sense, right? Epsilon outside. Then basically, and Alice is doing this experiment at space-like separation from this, whole process. Then Alice is going to be decoherent in a very similar manner up until the light travel time between her and the black hole. So she's going to decohere for some amount of time until she can see that a black hole has not formed, and it's a fuzzball. So that's not obvious from what I just said, or any of the calculations I just said, but it is true that that's what would happen. So for a fuzzball, that light travel time is extremely long, right? Because it's epsilon. I assume you guys would tell me better than I could tell you. So that light travel time is extremely long in that case. But for any body where the size of the star is bigger than the Schwarzschild radius, such there's basically no decoherence effect due to Alice doing the experiment in the same gravitational field, but just some massive body, bigger body. Does that answer your question?
Yeah, one way, maybe I'll sound like, you did this in 5 dimensions.
Yeah, any dimension. And also for massive or massive. Well, you do get an infinite. If you take a body and displace it in any number of dimensions, you can leave it there forever. The same calculation goes through, and you always get an infinite number of photons into the black hole. Yeah. No, I just said everything for photons. The same story is true in gravity. Yeah, you can do it in 3D as well. But not the gravity. You need radiation. Yeah. So you can do it in 3D.
You could do it in any 4 or higher dimension for anything.
Okay, so let me maybe say so. Now, okay, so there are 3 more things I can say, and I guess I'll just at least say one of them, and then we can take a poll. So the first one is, this is true. Everything I just said is true about any Killing horizon. So in particular, Rindler horizons in flat space-time or cosmological horizons, as will be apparent in the next slide. And the Rindler horizon is nice because you can just validate all of the calculations. I mean, everything I just said, you'd be worried about. Maybe I'm doing quantum field theory in curved space-time. That sounds hard. Why not just do quantum field theory? I mean, we all know how to learn how to do quantum field theory in flat space-time. Can you just do the same kind of calculation in flat space-time just to validate everything you're saying? Okay. And so you can just repeat the exact same story. So now the notion of stationarity, because I need a Rindler horizon, is that Alice is her lab is uniformly accelerating. Okay. And one can then analyze this effect from both the co-accelerating frame and the inertial frame. Okay, which I'll just briefly go over now. So what am I thinking of? Well, Alice's lab and her creating the superposition and then recombining it back together is all done in this uniformly accelerating lab here in some Rindler wedge. Okay, and as we all learned, in elementary school or something, that you see Alice's lab will see a Rindler horizon, which is a planar null surface in this case. Okay. So this is the similar picture as I gave you before, where Alice is separating and recombining the particle in her lab. This is the co-accelerating frame, okay? And the Rindler horizon is now a planar surface. The cross sections are, R2, they're planes now, where V here again is the same kind of affine time that I was telling you before. That's exponentially related to the proper time in her lab. And Z now is the coordinate that's telling me the distance from the horizon. Okay. And the exact same calculation goes through. So the radial component of the Coulomb field is now replaced by the Z component of the electric field as registered on the horizon. That's what Alice creates when she moves, and that's what Alice changes when she adiabatically moves the superposition in her lab. This A, capital A, is now, this is now a divergence on the R2, on the planar cross sections of the Rindler horizon. So this capital A indices are like X and Y coordinates now. But the same is going to be true where she's going to generate horizon radiation due to the motion of this body that she has in the exterior. And you can then exactly calculate the expected number of photons produced in this displacement, and it's again going to grow linearly in the proper time of her that she displaces the body, as before, where A is the acceleration of her lab. Okay, so this is just to say that I wrote this in such a way that you don't have to think too hard. It's exactly the same calculation. Okay. So you can do the exact same thing. And again, the presence of the Rindler horizon is going to force Alice to radiate soft Rindler photons. These frequencies go like 1 over affine time. So they're exponentially suppressed in the proper time of her lab. And the superposition is going to be decohered in a finite time. Okay, that you can just calculate. Okay, well, again, what's the point of this? Well, we can also compare to the inertial perspective, which one can do with considerably more effort. So it's, this calculation I was able to flash up on a slide very easily, and it's very quick. This calculation, I wouldn't even want to subject you to. It was, a mess in some sense to be able to get all the angular. I mean, it was really, really complicated. But this would be, if I was just doing regular, quantum field theory in flat space time and wanted to calculate what the expected number of photons are, I can just calculate what they are due to this process from the conventional, Peskin and Schroeder, inertial perspective. And one can compute the expected number of photons, and indeed, you get the same exact answer, which is that the expected number of photons now, as registered at scry, are linearly growing in time. And now, just due to the fact that an inertial observer is relatively blue shifted from the accelerating, from Alice, these photons, even though they were low frequency with respect to Alice's, to a co-accelerating observer, these are now going to be hard photons as viewed by an inertial observer. So they'll be exponentially. So these, I wouldn't want to be this observer as sitting out. Yeah, go ahead.
So, but in her frame, she's going to like from past infinity to plus infinity. So she's like
the experiment is done in a finite proper time. So she's not ever hitting null infinity.
But why she's doing this, she needs to keep accelerating.
Yeah, her lab is uniformly accelerated.
So she would be in a terminal state.
Yeah, good question. So, yeah, well, I can explain. Yeah, so the basic punchline is: would you be worried about decoherence from her doing?
I just want to know if the decoherence is terminal decoherence, or like she has a system superposition in a terminal band.
That's a great question. And why don't I? Well, I put it after the summary or whatever. The basic punchline is no. You can calculate the effect due to the even in the black hole case, you could be worried that black holes are famously radiating, and is this decoherence just the same as the decoherence due to the collisions with the Hawking quanta that Alice would be subjected to? And the basic point is no. I mean, the wavelength of those photons, even in this case, would be of order A. I mean, in this case, and in the black hole case, the wavelength of those photons are of order m. And if Alice's superposition isn't of order the size of the black hole, then these photons are really inefficient at decohering Alice's particle. And the same is true in this case. I don't want the size of Alice's superposition to be of order the distance from the horizon.
They're saying that there are kind of two effects.
There are two effects, and there's one that dominates when you're extremely close to the horizon. That's this one that you're worried about. And then this effect, which always exists whenever you're basically, well, it's always going to be there, no matter what.
So there's like, okay, we are in a terminal state, so there's a decoherence because we're in a terminal state.
Yeah.
But we're seeing that there is a horizon, we're also.
And this effect,
the
decoherence, is much faster than the one that you were just worried. This one that I'm
Because the temperature is so low.
because the temperature, the wavelength of the photons are just cannot decohere Alice more efficiently than the decoherence from this process. Go ahead.
Why does it matter that you think really is hard here? Is that hard versus soft feedback region?
It doesn't matter except for you. I'm just telling you what an inertial observer sees. Okay, so there are two things I could say: the cosmological story, and you can also talk about the bobs inside the black hole. Should I just wrap up, or which one? Okay, so then I'll just wrap. So then, let me end here. Okay, so the basic point, well, you can do the same calculation for cosmological horizons and so on and so forth, and you get the exact same decoherence for any superposition that Alice makes in the presence of such a horizon. You could also be worried or question or want to know about the Bob side of the story. The Bobs are making measurements inside the black hole. How is that related to the decoherence of Alice? I guess just look for a paper that'll come out shortly where you can basically relate the measurements made inside the optimal measurements rate inside the black hole to the decoherence that Alice suffers in the lab. The basic punchline is there is a sense in which the Bobs inside the black hole are making somewhat optimal measurements to achieve the decoherence that Alice gets in the exterior. Okay, but I won't go any further and then just say that, well, I think the fact that black holes and cosmological horizons, will eventually decohere any superposition in their vicinity, in the same spirit of Feynman in trying to understand what such objects, the nature of such objects in the fundamental theory may behave like, should be of fundamental significance to our understanding of such structures in the fundamental theory. Okay, so I'll just end there.
So you did calculations with the thermal states, and you
Yes.
actually see that the.
Yeah.
results are
Here, so, yeah, so you can do, so this is the Unruh version. You can do the Hawking version as well. So, but the collisions, the decoherence to the thermal, the collisions with the thermal bath is given, the time scale of decoherence is given here, where note explicitly m, the mass of Alice's particle enters because she's colliding with the thermal photons that are decohering her. And well, the first thing is that these are distinct effects. So the first question that you're asking, which is, are these the same? The answer is no. The second is that if the size of Alice's superposition is bigger than the charge to mass ratio of her body, which, as I mentioned before, has to be the case because vacuum fluctuations will always spread me out by a charge radius, by charge to mass ratio. The size must be bigger than this. It's straightforward to then compare these two terms and find that as long as the size of my superposition is much smaller than the thermal wavelength of the photons that are being emitted from the horizon, then this thermal decoherence is much, much longer than the radiation, and then the one that of our effect. And more generally, basically the same calculation in the cosmological case and the black hole case shows that the forced emission of soft gravitons and photons due to the presence of the horizon always decoheres you faster than the thermal radiation, as long as your superposition is smaller than the wavelength of the photons that are being created from the horizon.
No.
Wait.